You might ask why we want to study the continuity of functions. It's a subtle point, but we are really going to take a look at it now in talking about connected sets. Continuous functions take sets of x values and map them to sets of y values. But more than just mapping some x coordinates to a set of y coordinates, or mapping the domain to the range, continuous functions map or relate connected x sets, so sets of x values that are connected, to connected sets of y values. So from this picture we see that when x is a, we get f of a. When x is c, the output produces f of c. And when x is b, the output is f of b. In other words, all of the x coordinates between a and b will be connected to all of the y coordinates between f of a and f of b. This leads to a really important result called the Intermediate Value Theorem. The Intermediate Value Theorem for continuous functions says that if a function is continuous on a closed interval from x equals a to b, then the function takes on every value between f of a and f of b. In other words, if y naught is between f of a and f of b for some x coordinate which is contained inside the x interval, then that y naught value has to be f of c. That's confusing. Let's draw a picture. If we have a function like this, and we have an x coordinate here called x, let me draw it with axes, I think it'll be a bit clearer. If we have a function defined on a closed interval, so this is x equals a, and this is x equals b. And so we have the output values are called f of a and f of b. Then if we know that there is some y naught coordinate which is in between f of a and f of b, then it has to correspond to some value c which is in between a and c, a and b, along the x-axis. In other words, what it really means is if you have a function that goes from a height of f of a to a height of f of b, then it's saying that every height in between must be taken on by the function, if that function is continuous. In other words, the function can't skip from a height of f of a to a function of f of b without taking on every intermediate value, every value in between the two known y values. If the function's not continuous, then yes, the function can jump without taking on all the intermediate or in-between y values. But if the function is continuous, then the function will take on every single value in between the lowest known y value and the highest known y value. Does this mean that the function won't go any higher than the highest known value? No. Does it mean that the function won't go any lower than the lowest known value? Also no. But what it does mean is that every value in between the lowest known y value and the highest known y value on a continuous function must be taken on by the function. All right. Here's an exercise. Given values, a table of values for a continuous function, f of x, and it's key here that the function is continuous, that where must the function have x-intercepts? Well, recall that x-intercepts are values of x that make y 0. So values of x that make y equal to 0, well, we can see immediately that f of negative 5 is 0. So f must have an x-intercept. At x equal to negative 5. When we take a look in the interval from negative 5 to negative 3.2, we know that the x value was 0 and now it's negative. We don't know if the y values rather have gone more positive and then back down to negative or not. Similarly, when x goes from negative 3.2 to negative 2.9, we don't know what's happening to the y value's sign. Maybe the y value is changing sign from negative to positive. Maybe the y value is at negative 100, and then it goes to a height of negative 2. Well, it can go from a height of negative 100 to a height of negative 2 directly. Or it could go lower, or it could do a whole bunch of other things. It could even go higher, which means that if y goes higher than 0, or than negative 2, it may reach a height of 0, in which case there may be x-intercepts between negative 3.2 and negative 2.9. But we don't know that. It may happen that y takes on a value of 0, but we don't know for sure that it does. Meanwhile, when x goes from negative 2.9 to negative 0.8, y has to go from a height of negative 2 to a height of 3. And for a continuous function, there is no way to go from a height of negative 2 to a height of positive 3 without taking on all of the heights in between. And the important height for talking about a y-intercept, rather the important height for talking about an x-intercept, is the height of y equal to 0. So when x goes from negative 2.9 to negative 0.8, y goes from a height of negative 2 to a height of 3. Does it go directly there? Maybe not. It may go down first and then up. It may go higher than 3 and then down. It may actually go like this many times. But we know that there is at least one x-intercept between negative 2.9 and negative 0.8. So therefore, at least one x-intercept between or on the interval for x contained from negative 2.9 to negative 0.8. Furthermore, we have no sign change in the y-coordinate from 3 to 1 when x is negative 0.8 to positive 1.2. Maybe y changes sign, maybe y equals 0, but maybe not for sure. When x goes from 1.2 to 1.23, y changes sign from positive to negative, and therefore y must take on every height between positive 1 and negative 0.1, including a height of 0. So there must also be at least one x-intercept, also for x contained from negative 0.1 to 1, and there's no sign change in y from negative 0.1 to negative 2, so we don't know for sure if there's an x-intercept between 1.23 and 7 for x. So we know that at x equals negative 5, there is an x-intercept, and there is at least one x-intercept on the first interval as well as the second interval.